Good morning, folks. How are you? Hope you're going well. Welcome to week 5 of PMGT2851, the project analytic course. Today, we are going to focus on a really important part of diagnostic analysis. This is the second type of analytics. Last week, we went through descriptive, and this week, we'll be looking at diagnostic. Up until now, we have mainly looked at what has happened in a data set. Today, we shift gears and start exploring why something has happened. Analytics gives us the tool to uncover root cause, identify unusual patterns, and reason through what might be happening behind the scenes in a project. Both myself and Dr. Jin will be guiding you through a mix of theory, examples, and practical techniques that you can apply to real project scenarios. So let's quickly remind ourselves where we are in this course. Over the past 4 weeks, we covered introduction, data basics, fundamental of analytical tools, and descriptive analytics. Today, the topic is diagnostic, which acts as a bridge between describing the data and predicting data. Next week, we will hear from an industry guest partner or guest speaker, and then we will progress towards visualization, predictive, and prescriptive, and following that is the automation. All of this leads into your group assessment and finally quizzes on week 13. Understanding diagnostic analysis strengthens your ability to explain variances in project performance, which is essential before we move into forecasting and optimizing project outcomes. So what is diagnostic analytics? Diagnostic analytics focuses on uncovering the reasons behind observed outcomes. We typically follow three categories of diagnostic thinking. First, we identify anomalies, those unusual values or patterns that don't match our expectations. So, for example, if in sales, if a sales increase in a particular region despite no change in marketing activity, that's an anomaly worth investigating. Why it's happening there? Second, we drill down or conduct discover analysis that might involve examining additional data sets, internal or external, to help from potential explanation. For instance, maybe there was a certain regional trend or competitor issue we need to consider. And third is what we call is causal relationship. This is usually where statistical tools comes in. Techniques like probability theory, regression, filtering, and time series analysis help us uncover hidden stories in the data. The goal is not just to observe the correlation, but to identify meaningful drivers behind performance changes. In project management, diagnostic analytics is increasingly being used to support decision making. Historically, project decisions were often based on intuition or retrospective discussion. But with analytics, we can bring statistical evidence into those conversations. A great example is post-implementation review or your PIR in projects. These review often ask, did a particular action or lack of action cause a cost overrun or schedule delay? For example, could the project have saved a million of dollars if a certain decision had been made earlier? So something like that. Diagnostic analytics is already heavily used in construction where cost deviations and schedule risk need careful justification. But it's just as useful in IT projects as well, organizational change, business transformation, and many more. Anytime we need to understand why something has happened, diagnostic analytics comes into play because it's an essential toolkit. One of the key thing in diagnostic analytics is hypothesis testing. Um, let's unpack this clearly. What is a hypothesis? A hypothesis is simply an assumption that we want to test. We begin with a null hypothesis, or we call it H0, which assume nothing unusual is happening, that any observation or due to chance. That's where we start with. For example, the null hypothesis may say that the average cost of task has not changed. The alternate hypothesis, where we call HA, is what we are trying to determine. It suggests that the observed result is not due to chance, but that something meaningful has occurred. Hypothesis testing allows us to statistically evaluate whether we have enough evidence to reject null hypothesis in favor of the hypothesis that we are testing, which is your alternate hypothesis. In project term, this means we don't need to rely only on our gut feelings. We can use data-driven evidence to justify our claim. So now let's look at what p-value is. A p-value tells us how likely it is that what we observed happened by random chance. A low p-value, which is typically 0.05, means the probability of the result being due to random chance is very low. So we reject the null hypothesis. This suggests that something genuinely changed. A high p-value doesn't prove the null hypothesis is true. It simply means we do not have any evidence to challenge it. In project setting, p-value helps us to identify whether the performance issue, delays, or cost variation are statistically meaningful. When testing hypothesis, we must decide whether to use one-tailed or two-tailed test. Make sure you understand this one-tailed and two-tailed. A one-tailed test checks for a statistical effect in a specific direction. For example, if we want to test whether male salaries are higher than female salaries, we use one-tailed test. A two-tailed test checks for any differences regardless of direction. Example could be, are male and female salaries different at all? Choosing the correct test ensures accurate interpretation and avoids overstating or understating statistical significance. Let's look at what t-test is. The t-test is one of the most widely used tools in diagnostic analytics method. It checks how significant the differences between means are between groups, time periods, and condition. If the difference between two averages is large, the t-test helps us check whether it's statistically meaningful or simply the result of randomness. It is important to know the difference between t-test and z-test. When do you use z-test? The population distribution is normal, the population standard deviation is known, and sample size is large. And when to use t-test? When your population standard deviation is unknown and the sample size is small and usually less than 30. And in project environment, t-tests are more commonly used because population level information is rarely available. So the slide that you're looking at is the p-values log chart for normal distribution. This visualize how p-value correspond to tail areas of a distribution. Critical value represent cutoff points where our test statistics become significant. In normal distribution chart interpretation, a p-value 0.5 typically indicates that data significantly deviates from a normal distribution, meaning it is not normal. When a p-value is greater than 0.5 suggests there is not enough evidence to reject the normality, allowing you to assume the data fits a normal distribution. What does a t-distribution shows? The critical values for t-distribution. So the t-distribution is especially important for small samples as the degree of freedom increase. The t-distribution approach the normal distribution. Understanding this concept helps you to interpret statistical output more confidently. Okay, now let's look at an example. A project manager in a large company claims that mean salary of company's project managers is $85,000. A random sample of 33 project managers has a mean salary of $83,500. So with the standard deviation given as $7,200. If alpha is 0.5, let's test project manager's claim. So what is the null hypothesis here? Null hypothesis is greater than mu is greater than the mean is greater than or equal to $85,000 is the null hypothesis. But alternate hypothesis, we got to check if mean is less than $85,000, which is either it's $83,500 or less. So how do we calculate z? The z as a formula, z equals x minus u divided by standard deviation and divide by square root of n. So z, you get it. X is your the mean salary of 33 project managers. The random sample is what you take. 83,500 minus your $85,000 divide by 7,200 is your standard deviation with the square root of 33 project managers, which gives you minus 1.02 1.20, which means you see the p-value is on the negative side. Using this z table, find the probability of p-value, which you get 0.1151, which means as the p-value is greater than or equal to 0.05, we accept the null hypothesis. We have enough evidence to support that project managers claim that their mean salary is $85,000. That's how we do. Let's do a t-test one. In this scenario, a resource claims a task takes 20 days, but when we look at similar tasks, the average is 18 days with a standard deviation of 2 days. We test a t-test and calculate t coming as minus 3.16 with 9 degree of freedom. The critical value at 0.05 is minus 1.83. Since minus 3 is lower, we reject the null hypothesis. This means the 20-day claim is likely inaccurate. So the third example what we are looking here is we are testing whether a proposed budget of 2.5 million is reasonable or not. Using historical data for 30 completed projects, we run a Z test. The p-value we get is 0.018, which is below 0.05. So we reject the null hypothesis. This means the proposed estimate is probably incorrect and the project is likely over or under budget. So let's do the types of t-test. There are three main types of t-test. One sample t-test compares one group to a known value, and the other one is the independent sample t-test which compares two different groups, and then the paired t-test compares the same group across two main periods. These tools help evaluate training impact, resource performance, or before and after project outcomes. Now let's look at what parametric and non-parametric test examples are. Parametric tests rely on assumptions about population parameters, which is your normal distribution or equal variance, and analyze interval and ratio data using means, making them more powerful. However, a non-parametric test make few assumptions about data distribution using ranks or medians, making them ideal for small, skewed, or ordinal data. Comparing two dependent or related samples, we use t-test. A paired t-test is a statistical procedure used to determine if the mean difference between two sets of observation is zero. Typically used for before and after studies or matched pairs on same subjects. It checks if the average difference is significant, helping to eliminate individual variation. And if you look at independent samples, we use independent t-test. An independent t-test is nothing but an inferential statistical test that determines if a significant difference exists between the means of two unrelated or independent groups. It is used to compare continuous dependent variable across two distinct categories such as testing if average salaries between men and women. Interpretation. We did this in the last class as well, last week. When interpreting data distribution, analysts often examine whether the data is highly skewed, moderately skewed, or approximately symmetrical, which is your normal distribution. A highly skewed distribution occurs when a large number of observations are concentrated on one side of the distribution, while a few extreme values extend the distribution in one direction. A moderately skewed distribution shows some imbalance, but the data is still relatively concentrated around the center. An approximately symmetrical distribution is one in which the left and right side of the distribution mirrors each other, forming a classical bell-shaped curve. Understanding these patterns helps analysts to interpret descriptive statistics or diagnostic data or more accurately. This slide shows you the skewness and kurtosis. The skewness tells us whether our data leans right or left. This is important when selecting statistical test. So if you look at between, if it's the value is between -1 and -1, 1 by 2, which is half, or +1 by 2 and 1 plus 1, which is, you can call it, the distribution is moderately skewed. And if it's fall between -1 by 2 and +1 by 2, which is approximately symmetry, which is your normal distribution. ANOVA. A ANOVA test, ANOVA is nothing but analysis of variance test, is a way to find out the difference between your testing groups. In other words, they help you to figure out if you need to reject the null hypothesis or accept the hypothesis. This practical example uses ANOVA or ANOVA or analysis of variance to determine whether differences satisfaction levels across different projects might explain why 3 employees left. If walks through preparing the data in Excel and running one-way ANOVA, if p-value is below 0.5, it suggests dissatisfaction is likely related to projects they are assigned to. So if you're doing a comparison of two, three or more related samples or unrelated sample to do a t-test, we use a repeated measure ANOVA, which is analysis of variance. What is it? What is the test is for? It is a statistical test used to compare means across three or more conditions, time points, or trials where the same subject participate in all conditions. It detects changes in independent variable over time or under different treatments, reducing error variance by controlling for individual differences. So if you are comparing three or more unrelated samples, what test we use is called one-way ANOVA. One-way ANOVA is a statistical test used to determine if there are significant difference between the means of three or more dependent variable, and it evaluates one independent variable, a factor with different levels, to see if it affects a continuous dependent variable. Running one-way ANOVA helps us to see whether the project assignments contributed to dissatisfaction. Okay, let's see what correlation is. Correlation is measure of how strongly two variables move together. The values range from -1 to +1. A key reminder to note here is correlation does not imply causation. Just because two variables move together doesn't mean one causes the other. But correlation is still incredibly useful to identify a potential relationship worth further exploration. And that's the part of our class, which concludes our session on diagnostic analysis. We covered hypothesis testing, p-values, t-test, ANOVA, correlation, and numerous projects related example. And hopefully we'll do the activities in class, and you guys should be able to understand how the p-value, t-test, and hypothesis can be done. And yeah, see you on Friday. Thank you guys. Have a good evening.